Dan Wallach of DARPA, thanks very much for joining me. It's great to have you here. What is the Resilient Software Systems capstone, and what will you do with that?
So DARPA has been looking at software for resilient systems. How can we improve software security? And we have a number of programs in our portfolio that have taken different stabs at this problem. The capstone is a series of tech transitions where we're working with our military partners to get this stuff into production. So an example of this, I'm working with Navy submarines, and I can't go into the exact details, but I can tell you that there are some legacy systems and there are some modern systems, and we need to connect them in a safe way. And so we're using some safe parsing technology, which is meant to build what amounts to a firewall that can protect some of the sensitive parts on the inside from some of the parts on the outside. And that's a tech transition that will have a real impact.
Are there common threads in the systems where you have to connect some legacy software with something that's pretty new and cutting edge?
So in the world of software engineering, you never want to start from scratch. You're always taking a legacy system and adding new functions and new features. And so the challenge in software engineering, or really any kind of engineering, is how to achieve what you need to have, but you don't have the luxury of starting from scratch. So we need to incrementally add features while we're incrementally improving security.
There are a couple of other items in your portfolio that I think are really fascinating. Assured micro-patching is what?
So imagine the scenario where you've lost the source code. All you have is the binary. You'd think that, why would that ever happen? It actually happens relatively frequently. So all you have is the binary that's running on a computer, and it has a bug that you need to fix. Now what? So the point of assured micropatching is to provide the developers better tooling to disassemble, make the change, and reassemble it, and have a very tiny set of changes, along with some assurance that they didn't accidentally break something else. Because all you have is the compiled version of the program. How do you know that your change won't have some weird side effects? That's what AMP is all about.
That strikes me as much forensic work as technology work. Is that a fair assumption?
It's really reverse engineering work. And so we want to make it easier to reverse engineer the software to be able to find where you need to fix it.
Another one, SafeDocs. Tell me about SafeDocs.
So SafeDocs is trying to address the problem where the very outside of the software, what we call the attack surface, is typically receiving data from the outside, parsing it in some fashion, going from bits to data, and then it reaches the inside of your program. That's where a lot of the attacks happen. So SafeDocs says, couldn't we write down a specification of the data format? These are the messages, this is a length, this is a color, this is a value, and then have it automatically synthesize the parser in a way that the parser won't be exploitable. It'll just say, that's a message that I don't recognize, sorry, as opposed to that being a source of security vulnerabilities. So SafeDocs did all of that. They built a number of tools that can very efficiently and securely parse data that's coming in from the outside. That's the technology that we're transitioning to Navy submarines right now. And we're looking at a number of other possible transitions.
Are there common threads in these items in your portfolio and the others that we don't have a chance to talk about today in the way that you develop them or the way that users in the department let you know that they need them, so on?
So the thing that all of these have in common is that we're trying to do sophisticated engineering of one piece of a much bigger puzzle. Each of these things, whether it's SafeDocs or AMP, is trying to say, this is a pain point. And how can we use the most sophisticated computer science to deliver tools that can be usable by the defense industrial base to help improve its security?
What overall do you see as the direction that the projects that you're working on are going? What are trends that you anticipate to see?
So the broader trend is, well, really two trends. One is the use of formal methods. It's not enough to say that we've built a tool that seems better than the past. We want to have a tool that we have a formally proven assurance case that this tool will solve a problem and guaranteed not to have new problems. So formal methods is one big trend. The other big trend is, of course, artificial intelligence. How can we use AI tools, which are surprisingly good at writing software? But the problem is that they hallucinate sometimes. So the formal methods and AI can play together in a nice way, that we can use formal methods tools to double check that the AI is not hallucinating. That, I think, is where the big trend is going to be.
What will be the key to that interaction and to using that interaction successfully in your view?
So this is an open research problem. How do we take these two completely separate streams of academic thought that have their entirely separate histories for decades, and how do we usefully combine them together? That all by itself is an open research challenge.
It's great to have you here. Thanks for joining me today.
It's a real pleasure.